Okay, let's go ahead and get started. Athel's going to do the formal introduction of Miguel. So I just wanted to say, first of all, I'm Ed Seidel, the director of NCSA, and I'm really pleased to help announce the colloquium series. Miguel is one in a series of speakers. And just to point out, we work on this very hard. We have Anita Chan next week from the Department of Media and Cinema Studies giving, is it next week or 2 weeks? It's actually next week, okay. On networking peripheries, technological futures, digital memory, and the myth of digital universalism. So we have quite a wide spectrum of activities here. Miguel today is going to talk to us about black holes and black hole collisions. And I just want to thank Miguel. In case you missed last night's event, we had a wonderful kickoff of the 30th anniversary of NCSA, which actually goes back to, I think it's January the 16th or something, 1986. I forgot the exact date, but this is the 30th anniversary. And we have a nice exhibit at the Spurlock Museum, and there will be events there throughout the year coming up. And so last night was the sort of the major kickoff, and Miguel gave a wonderful public lecture on faster than light travel. Today's going to talk about things that are just as fun, especially if you work in black holes, but a little bit more focused on the science of general relativity, and Athel will give the introduction.
So it's a great pleasure to host Miguel, professor and director of the Nuclear Sciences Institute at UNAM at the moment, and has had a very distinguished career in this particular area in his career. Previously at the Max Planck Institute for Gravitation at Potsdam, completed his PhD in Wales and his undergraduate physics degree at UNAM itself. And we're very familiar at NCSA with the very great power of simulation and mathematical solution of intractable problems. But we also know that that very process is itself no simple exercise, often involving deep challenges in the problem, computer science, and in the numerical aspects. So Miguel will...
Thank you very much. So today I want to talk to you about numerical relativity, which is the field in which I've worked most of my career, or all of my career, and the binary black hole problem, which is related to this great discovery that was presented to us 3 weeks ago of gravitational waves detected for the first time. I'm going to apologize first to those of you who are not physicists, because when I prepared the talk, I thought most of the audience would be physicists, so there's a few equations there. I'm going to try and go through those quickly, and those who don't understand them, don't worry. I'll try to explain the important details later. So I just wanted to say a bit about relativity and what we do. So here comes the first equation, which is relatively simple, apparently. In relativity, we have this theory of gravity that tells us gravity is just the curvature of spacetime, and the whole theory comes back down to these equations, which are called Einstein's equations, which relate on the left is this thing G, this tensor G that represents the curvature of spacetime, and on the right we have this other thing called T, the stress energy tensor of matter. So it tells us that curvature is produced by matter. The equations look extremely simple, very innocent. They're actually very beautiful and conceptually very elegant. But this simplicity is extremely deceptive because these quantities are actually very complex objects. So when you actually write these equations in a completely general setup, it turns out there's 10 equations. That's what they're called Einstein equations, another equation. They're nonlinear, they're coupled, they're partial differential equations in 4 dimensions. And worse than that, when you actually expand them completely, they have thousands of terms. And I'm not exaggerating. You can do this in Mathematica and it comes out to about 3,000 terms. So it is really thousands of terms. So solving these equations is extremely difficult. And people have done it for decades. We have books of exact solutions of the equations, but it's a very difficult task. And many of those solutions don't really have any real-life applications. So that's why for the last 40 years, some of us have decided that we really need to solve these equations using simulations on a computer because the equations are so complex. And that's the field of numerical relativity. It's taking those very complicated equations and solving them in a computer for systems that are realistic. Because if you want exact solutions, you only have a few. You have solutions with high degrees of symmetry, static or spherically symmetric, maybe axially symmetric. If you're lucky, you do cosmology, they're homogeneous and isotropic to first approximation. But if you want anything more interesting than that, solving the equations is extremely hard. So we solve them on a computer. And that's the field of numerical relativity, For those of you interested in actually learning this in detail, this is just buy my book or buy Stu's book. Stu Shapiro. Buy both. Exactly. There's actually another book, and there's one that just came out about a couple of months ago by Shibata, which I haven't read, but it just came out. So there's full books of that have been around for a few years, so this is an active subject. For many years, there were no books. We just had to read the original papers, and that's what we all did. I'm going to go a little bit through the ideas and some equations, and sorry for those of you who don't really like equations. The main problem in numerical relativity is that Einstein's equations are very, very elegant and very general, and they are equations in space-time. So we live in space-time of 4 dimensions. And in those equations, space and time are equivalent. They're symmetric. And that's really very nice and very elegant, but it's difficult to solve them like that. Normally, one wants to solve a problem thinking, I have some initial condition, and I want to follow the evolution of the system in time. But that's not how the equations are written. So first, you need to break down that structure. You need to separate space and time. So we call that the 3+1 formalism, or the 3+1 decomposition, in which you separate space-time. You have this 4-dimensional block of space-time, and you slice it into 3-dimensional space and 1-dimensional time in the orthogonal direction. And we do that in a number of different ways. I'm not going to go through the details, but there's a series of functions that we need to determine to do that slicing. So one of the functions is really important. We call it the lapse function, and that tells you how time moves forward. Remember, this is relativity, and that in essence means that time can move at different rates for different people in different places, and you have to choose that. That is essentially a free function. You choose how time moves forward. That's the lapse function. You also have to choose your coordinates as something we call the shift vector, but I'm not going to stay on those details. That's not the only way to do it. People have tried other ways to do it, which are actually complicated conceptually. Instead of slicing space in nice 3-dimensional surfaces, you can slice it in cones, light cones. And that's this thing that I'm trying to represent here. That's another way people have tried to do it. Or this I won't even talk about because if you're not physicists, you won't understand, but there's yet another way to do it, which is very elegant. Once you've done that, you also need to identify things you're evolving. So this is a curved space, so you need to identify how to measure the curvature. And one thing is to take your curved surface, put a vector there, a normal vector, move it away, and see how it changes. That's a way to measure the curvature. We call it the extrinsic curvature, and you end up with an equation that gives you the extrinsic curvature as a time derivative of something else. So again, I'm just going to jump through this very quickly. But what I'm interested in, don't worry about this too much either, because what I'm interested in is the end form of the equations. These are the equations we end up with. So these are the Einstein's equations I showed you before. But they've been worked in this 3+1 formalism, and they look now much more nasty. And they're actually even worse, because here you have hidden this little quantity r, which is actually called the curvature tensor of space, the Ricci tensor, and this object is already completed, very complicated. So this thing expands a lot, and actually if you write this out, these equations have many more terms. But this is what we want to solve. These are the equations we need to solve. We call them the ADM equations. And those equations were derived in 1962. There's an interesting story about these equations, because these people, Arnold with Dessler and Misner, derived this system of equations in 1962 for quantum gravity. They were not interested in numerical simulations. They were interested in quantum gravity, and they needed to write the system, Einstein's equations like that, to be able to, because quantum mechanics needs time. It needs an evolution in time for it to make sense. So they needed to do this. But the equations look nice, so people trying to do numerical simulations thought, well, this is great. We already have a system that looks like the evolution of something in time, so let's use it. This is not the only problem. You also need to start your simulations. So if you want to evolve something, well, you need to start the simulations and you need to give initial data. So for black holes, we apply a very clever trick for starting the simulations. We actually represent black holes like wormholes. Those of you that were there last night, I mentioned the idea of wormholes, these tunnels through space that connect different universes or different regions of space. It turns out, as I mentioned also last night, that black holes have wormholes inside them. This is very nice. And you can construct black hole data, initial data, connecting universes like this. You can, for example, think of two black holes like two tunnels like that. If you do something like this, we call it Misner-type data. But you can do it differently. You can think that these two black holes connect to different regions totally disconnected. This is Brindle-Lindquist type data. For a long time, people like to use this initial data because it looks nicer. It looks very symmetric. Now everybody uses this. and the reason is that this looks much nicer, but actually doing it mathematically gets much more complicated. The expression for this is very complicated mathematically. This one is far simpler mathematically. And actually, it seems it doesn't matter because you see the difference is only inside the black holes. And we don't really care what happens inside the black holes. We care what happens outside. And the only difference was inside. So now we use the other one. I'm going to jump this because this was really thinking about this. So I'm going to jump that one. Now we have to also choose. It's not just the equations and the initial data. We now need to choose how we evolve time, as I was mentioning. We need to choose something we call the gauge conditions, which is choosing how time moves forward, this lapse function. How do we move time forward in different regions of space? And also how we move our coordinates from one place to another. This is called the shift vector, and this is completely free. And when you have completely free things in physics, it's sort of a double-edged sword, right? On the one hand, you say, great, I can do anything I want. The immediate question is, okay, now what do I do? What is a good idea? What is a good choice? And that's non-trivial. So people worked for a long time trying to get good ideas of these conditions, that from the 70s onward. A lot of that work was actually done here at NCSA, studying different conditions for the lapse function. The shift vector was ignored for a long time, not entirely. There were some ideas in the 70s, but then it was left like that, and it became very important again in the 2000 forward. Okay? So I'm going to just show you this one. This is one way in which you can choose how time evolves. Imagine here that you have a diagram in which you have a star. Say you have a spherical star, and the star is at the end of its life, and all the nuclear fuel has run out, so it starts collapsing because it's growing cooler, and it collapses into a point, a black hole. So this represents the collapse of the star as time goes by, so time is up, and eventually it reaches one point. All the matter collapses to one point, and you have a singularity there, and then you have a horizon, so a black hole is formed. That's how black holes actually are formed in nature, a dying star. And then if you want to move forward in time, as soon as you hit this place, the singularity, at the singularity gravitational field is infinite. When you get here, then you get infinite quantities in your solution. Computers don't like infinities. They start saying not a number and they stop. So that would stop your simulation. What you can do in a very clever way is to move time forward here, but then slow it down, slow it down, slow it down, but keep it up here. So your time moves like that, and eventually here it's frozen, and here it's moving. So this is an idea that you can use, and this is essentially what we do in practice. We choose time in such a way that it slows down inside the black hole and keeps moving out at a normal rate outside. So we have different ways of choosing those things. This has its own problems because, as you see, this thing is getting all extended here, and that creates problems on its own because it's a stretching of space in here. We also do similar things for the shift condition, but I'm going to jump that as well. And this I just wanted to mention to the physicists in the audience. The equations I showed are called the ADM equations. Those equations were derived in '62. And people were using them for a long, long time, more than 30 years. There's a problem with those equations that we didn't realize. Some very clever people did, but most of us didn't. Those equations are not actually well posed mathematically. Those equations have a problem at the differential equation level. For a long time, throughout the 80s and good part of the 90s, I would hear to a lot of people saying, well, the problem with our simulations is just that the computers are not big enough. And in part, that was true, but it wasn't really the true answer. The problem with our simulations was that the equations we were using were wrong. Not wrong physically. Physically, we're okay, but they didn't have the right mathematical properties that allowed us to simulate them in a computer. And a lot of people were starting to say this, not a lot of people, a few people were starting to say this in the 80s and early 90s. We wouldn't listen. So you would find that the numerical relativity community is very practical.
Just add a note. So Nakamura came to visit me here at NCSA in the about 94, 95 time frame. And he talked a little bit about his great formulation of the equations, but not very much. And so he knew he had a piece of gold, but he didn't want to really, so he wasn't going around saying everybody should use it, because he knew he had a really good tool.
Exactly. And so we didn't realize it was important. Some people did, exactly. Nakamura in Japan, and then Shibata later, they realized that the ADM equations weren't a good way to write the equations. They developed a new way to write them, but essentially that happened. They wouldn't go around and tell people use this, and nobody really paid much attention to them. Until 1999, when something very interesting happened, Stuart Shapiro and Thomas Baumgarten took essentially the system developed by Nakamura and Shapiro with a few modifications, and they did a series of tests comparing that system with the original ADM system in many different situations, and they showed that the new system was far, far, far superior to the old system. That was 1999. And they did say, use this. That was the difference. So the system was known as BSSN since then, from Baumgarten, Shapiro, Shibata, and Nakamura. And many 3D production codes use today that formulation. It's not the only way to write the equations. There are other ways to write the equations. Other codes use a different approach. But I wanted just to mention this one, because this is one in the one in which we worked very, very hard for many, many years. Actually, the name BSSN, or the acronym BSSN, was invented by Bernd Bruckmann and myself. People didn't call the system that before us. Then imagine you have your system of equations, you have your initial data, and you want to solve them in a computer. So I'm just giving you a very, very quick cartoon of what we do. We have a very complicated system of differential equations. Those are very difficult to solve. But the computer, in general, doesn't solve differential equations. What it does is it does numbers. It adds, subtracts, multiplies, and divides. So you need to translate your differential equations into a system of multiplications and sums and whatever. So we essentially separate space and time into a discrete mesh. We put a discrete mesh of points in space and a discrete time step in time. We use this is a method called finite differencing. There are other variations of that, but that's the easiest to understand conceptually. And we approximate mathematical derivative operators in each point with just sums and subtractions and divisions. So this is called finite differences. So we turn one equation, one differential equation, into a bunch of algebraic equations, one per every point in the grid. Okay? So imagine you have a grid with 100 points in each direction. That's already 1,000,000 points in 3D. So if you had one equation, you just turned it into 1,000,000 equations. The difference is the one equation was a differential equation. Now you have 1,000,000 equations that just involve some multiplications and additions. Computers are good at that. They can do a lot of operations very quickly. We can't. So that's what we use computers for. This is non-trivial. I just went through it very quickly, but it's non-trivial. Finite difference approximations are an art in itself. You're never exactly sure how to do them. There's three properties that are very important, and you should have an idea. You need to show that your equations are consistent with the original equation. That means that if you disappear this spacing, you let it go to 0, then you recover the original differential equations. That's called consistency. That's usually trivial to show. Not always, but in most cases it's pretty trivial to show. You need another property which is really what you want. That's convergence. That means that in this same limit, when the increments go to 0, your solution of this approximate equation approximates the solution of the true system of equations after a finite time. You see, they're different. Here, consistency just means that you recover the original equations in the limit. This means you recover the original solution in the limit. It's different, okay? And this is the original solution after a finite time. But if you make these things go to 0, a finite time actually means an infinite number of time steps. So consistency, in a way, means that the error that you accumulate in an infinite number of time steps is still 0. That's consistency. And there's another property, that's stability, that's really what always worried us. That is, you might find that your original equation was really simple and had very beautiful solutions, but when you do a numerical approximation, it blows up. It becomes infinite very quickly. That's called an instability. So you don't want that to happen. And there's a very nice theorem that tells you that if you have consistency and you have stability, then you have convergence. That's called Lack's theorem. It's very elegant. And this is what we want. We want convergence. We want the solution of the equation. So if you can show this, and this is usually very easy to show, and you can show that, which is not that easy to show, but you have some idea of when it might happen, then this is guaranteed. Okay? That's what we do. And this is really what makes any kind of numerical solution work, this theorem. Okay? Because if you show that the thing is converging, then you know that it's converging to the right solution. And that's what I usually tell people that are only doing exact solutions. Very often I give a talk like this, and people in the audience are only used to doing exact mathematical solutions, and they tell me, how do you believe the numerical solution? It's probably only error. I say, no, because we checked consistency, we checked convergence, we checked stability, so we know that the thing is working. Okay? I'm going to go to the main part of the talk, actually, because it's the more interesting for a general audience. I'm going to talk about black hole collisions. Black hole collisions is the most important problem we try to solve in numerical relativity. You might think, why? Black holes seem like very esoteric objects. But black holes have one nice advantage. They happen in vacuum. A black hole has no matter. All the matter has fallen into the singularity. There's no matter around. So there's solutions that involve no matter, only space, only vacuum. And this is the interesting thing, because if you want to study a star, then you have to deal with gas, you have to deal with the plasma, maybe you have to deal with neutrinos, and a lot of very complicated things. You want to study a black hole, that's all gone. There's nothing. It's just pure space. So the equations actually simplify a lot, even though the black hole is a complicated mathematical object, an abstract complicated mathematical object, the equations are actually simpler. So the problem we wanted to solve for now 50 years, but it was solved 10 years ago, was two black holes in orbit around each other. We weren't even entirely sure if these systems existed, well, we thought they might. So you have two black holes, they're in orbit, like stars around each other. When they're in orbit, general relativity tells us that they emit gravitational waves. They're moving very fast, they're very compact masses, they're accelerating. That produces gravitational waves that go out. The gravitational waves take energy away, so the black holes will approach each other. This is what we would call the two-body problem in general relativity. The two-body problem in the theory of gravity of Newton was solved very early on. Actually, Newton solved it on his own and never told anyone for about 20 years. That's an interesting anecdote. Until his friends went knocking at his door in the 1680-something and said, oh, Mr. Newton, we were thinking about maybe the theory of gravity, maybe the force of gravity goes as 1 over r squared. If that's true, we want to solve the trajectory of two bodies. Do you know how we can do that? And he answered that those are ellipses. And they say, how do you know? I solved it 20 years ago. But he never told anyone. So the two-body problem in Newtonian gravity was solved immediately. And what you find is that two bodies with gravity will go around each other in an ellipse, okay, essentially. The two-body problem in general relativity was not solved until 2005 in full detail, because the simplest case is two black holes in orbit. And they emit gravitational waves, so they don't stay in the same orbit. They move towards each other. Eventually, they collide. It's a very complicated system. Okay? So that's what's called for many, many years the holy grail of numerical relativity. Do the simulation of two black holes in orbit around each other, complete all the way through until you merge into a single black hole. It was a very, very difficult problem. The first people that tried to solve that problem were actually very brave. Hahn and Lindquist in 1964. That's the year I was born. So it's a long time ago. They tried to study not the collision in orbit, because at that time, imagine the computer was 1964, okay? The memory and the speed. So the problem of two black holes in orbit was very complicated, so they tried to solve the problem of two black holes hitting each other head-on. You just let them loose and they hit each other head-on. That's easier, because if the two black holes are the same and they just hit each other head-on and they're not spinning themselves, then you have a symmetry around the system and along the line that connects the two black holes. You just go around and it's totally symmetric. That means you can solve the problem only in 2 dimensions, not in 3, which is easier on a small computer. So they did that. In 1964, the name black hole didn't even exist. The term black hole was invented by Wheeler in 1968. So it was 4 years before the name existed. So they actually called this paper the two-body problem in geometrodynamics, which is a name we don't use anymore, but it's a name they gave to general relativity at the time, the dynamics of geometry. Now it sounds dated. At the time I guess it sounded really very modern, but now it sounds dated. But that was the name of the paper. They didn't even call these things black hole. This is the setup they had in mind. Two black holes, again represented by a wormhole, but a wormhole that goes to the same universe, not to another universe, as I showed before. And they really tried to enforce this condition, but they didn't understand many things. They didn't even use ADM. The ADM equations were from 1962. They already existed, but they didn't use them. They used a very complicated setup. They didn't understand much about coordinate conditions. It was really complicated, so they weren't very successful. But it was the first ever attempt to do black hole collisions in 1964. The next attempt came in the 70s, and it was done by Smarr and Eppley. in the mid-70s. They took again the same system, two black holes colliding head-on. By then, they already called them black holes. They knew the ADM equations, so they applied this new system of equations. The computers were much better. It's 10 years later. So they were much more successful. They again used very complicated setups, because for a long time, people thought that you really needed to use a very complex geometry and very special coordinates and everything really complicated. These are some pictures from their paper of the evolution of some of the functions of the geometry of space. So don't worry too much about the details. But again, there's two black holes colliding together. These simulations were far more successful, even though they weren't as good as we would have liked. But this was really the beginning of what I would call modern numerical relativity, using a modern system of equations, using a language that we understand today about how to choose the conditions, the lapse function, the shift vector, the different normal conditions, the different coordinate conditions. And they even tried to see if there were some oscillations of the black holes that we call quasi-normal modes. So they saw some hint of these oscillations of the black holes that would represent gravitational waves, but there was no true way to extract the gravitational waves at the time. And they had very large numerical errors and very large instabilities, but essentially it was really the beginning of doing the problem correctly. And this is a timeline of what happened since the beginning. So this problem took 40 years to solve. Okay? The first attempt, 1964, it was finally solved in 2005. So this is the ADM equations in 62. Hahn Lindquist first attempt in 64. Then the second time they did it, 1975, the head-on collision, Smarr and Eppley. As I mentioned yesterday, this in a way is the birth of NCSA, even though it took another 10 years. But the reason was that Larry Smarr had to go to Germany to do all his simulations because there were no supercomputers available to him in the US. And eventually he got tired of this, so he sent a proposal to NSF for a National Supercomputer Center for Academia, and that's how he got NCSA funded and created about 10 years after that. But this was the original motivation, colliding black holes. Then many things happened in the middle. At that time, Smarr and another physicist known as Georg, they developed new conditions for studying the geometry of the space-time, essentially for seeing how space and time advanced. Then there was a very nice review paper in 1979. All of us actually learned from that paper. There were no books, so we all read that paper, and we learned numerical relativity reading that paper. Then there was a suggestion in 84 by Unruh that since we're studying black holes and we don't care about the interior of the black hole, maybe, and all the problems with the simulations happen inside the black hole, maybe we just can cut out that from the grid. And since nothing comes out of a black hole, whatever you do inside doesn't matter. So if you just cut it, it should work. This is called excision and still used today in some codes. Then in the late 80s and early 90s, there was this group of people telling us you're doing things wrong, the ADM equations don't work, you should switch to a different system of equation that has nicer properties. Nobody was listening. I mean, John Massel was here for a while, and he was working with Carles Bona, and other people were saying the same things, but the community wasn't really listening. And as I was saying, we're a very conservative community and very practical. If it works, we use it. If it doesn't, we don't. And we didn't really care too much about the detailed mathematical explanations. We just wanted something that worked, so they couldn't convince us at the time. Then there was a really interesting time in the 90s, from 94 to 98. There was something called the Grand Challenge. It was an NSF-funded attempt that united several groups in the United States to try to solve, for once and for all, the collision of two black holes. Okay? There was a lot of money, a lot of postdocs involved, several institutions. In the end, they couldn't actually solve the collision of two black holes spiraling in. That took another 10 years, but many important advances happened at the time. At the time, there were done very beautiful simulations here at NCSA by Ed's group, that I'm going to show a few of those here. Still head-on collisions, but many ideas were tried and tested at the time. The head-on collision, some nice conditions for the lapse function, this idea of cutting the inside of black holes. Many of those things actually matured at this time. I wasn't directly involved with this because at the time I was in Wales and then Germany, and this was something that only happened in the United States, really, the Grand Challenge. So we weren't directly involved, but we knew many of the things were happening. Then some new ideas of initial data, 1997, 1999, this system, new system, BSSN, Baumgarten and Shapiro showed us that this idea of Shibata and Nakamura from the late 80s and mid-90s really worked, and we should use it. And we finally paid attention. So we switched to this system. First, the group at the Albert Einstein Institute, and then several other groups, even in the United States, moved to this system. And things started working much better. By 2000, a year later, we were doing the first collisions of black holes that were not head-on. They were grazing. So you have them slight offset, so they will collide with a slight angle. That's called the grazing collision. We were doing it in 2000. Then some people started doing an idea that was really nice, the Lazarus idea, which was the simulations are breaking down. So once your simulation is about to go unstable and break down, stop it, read data, and use a different code that only does quasi-normal ringing of black holes, an approximation to a final black hole, and try to extract the wave from there. So it was, they called it Lazarus because it was a way to resurrect a dead code that was dying. This had some important successes. Then we had some nice conditions for the shift that we were lacking, that were developed in 2002. That's very important. The shift vector, I didn't mention it very well, but the shift vector is a way to move your coordinates around. So you're evolving space-time, and your observers are moving with the flow of space-time with gravity. And if you have a black hole, the black hole wants to swallow everything. So if you have your observers moving around the black hole, they end up inside the black hole. It swallows them. And you don't want that because that means that all your computer now is solving only the interior of the black hole, which you don't care about. So you want to push them back out. And for that, we use a vector, a vector field that pushes the observers back out. So if you have a black hole, you need to contrarrest this inflow of things to push things back out. But only that, if the black hole is spinning, or if you have two black holes going around each other, then what happens is that these lines get all tangled up because they don't only fall into the black hole, they actually follow the spin of the black hole. So after a while, you have all your coordinate lines all tangled up around the black hole. You want to contrarrest that, so you want to push them back with our rotation. That's all done by this vector. We didn't know exactly how to do it. We had some ideas before 2002. But in 2002, we had a nice idea of a very simple condition for this vector that actually did everything we wanted on its own. It was actually very surprising because the initial thought was, we have this vector and we have these other quantities. There are three quantities, and maybe they're related. So just try to make them one equal to the other, or the derivative of one equal to the other, and see what happens. And it worked. It worked beautifully. I was very surprised by that, but this was a very important breakthrough. We had more simulations in this period, 2002 to 2005, trying to push the black holes further and further apart and try to do at least one orbit. So put them in orbit and see if we can do one. Okay? Very, very close together. We call those ISCOs and pre-ISCOs. This comes from the innermost stable circular orbit of black holes. So they're close enough that they wouldn't even give one orbit. They would just plunge, and you put them a bit further out, and they would take a little bit longer to plunge. We were trying to do one orbit. We couldn't do it for a while. It was a very difficult problem. The problem with the black holes is that they have singularities. They have singularities inside. And in singularity, everything is infinite. And computers don't like infinities. So what we used to do is you take that infinity and analytically take it out. You factor it out and just evolve the rest, which should be regular, and take the infinity out. But if you do that, you have an infinity sitting here, and then you take it out by hand, essentially, and deal with it analytically, then it's always there. It's always in the same point, because that's where you put it, right? And that means that if the black holes want to move, they can't, because you fix the center to a point in the grid. If the black holes want to rotate, they can't, because the center is fixed. But they want to rotate. So what you wanted to do is try to contrarrest the rotation, and you would use a system of coordinates that was rotating with the black holes. So from the point of view of the coordinates, the black holes were always in the same spot. Okay? And you wanted to keep them roughly in the same spot. That was extremely hard to do. In the end, it turned out we didn't need to do it. But for a while, we thought we did. So that's how we did these things. Even this first orbit, which was done in 2003 by the group of Bernd Bruckmann in Jena, was like that. It was the black holes fixed to the grid and rotating the whole coordinate system with them. And he managed to do about 1.5 orbits doing that. But you didn't see the black holes move, okay? They were glued to the grid. It was just the system rotating. That was 2003. And then in 2005, something magical happened. I'm going to show it in a minute. Frans Pretorius came along and did a completely different thing. He did a new code using totally different methods, totally different ideas, everything different from anything we had done in the last 30 years, and it worked. He managed to do black holes orbits, several orbits. They actually moved on the grid. He was cutting the interior of the black holes. He even started the simulations with no black holes. He started the simulations with some stars that we actually call boson stars because they're made of a strange thing we call a scalar field, but essentially two stars. But they were unstable. They would collapse and form a black hole very quickly. And then he would cut the interior of the black holes and allow those two holes now in the grid to move around, and it worked. That was 2005. For a while, we all panicked, I included, because we thought, wow, everything we've been doing for the last 20 or 30 years is wrong, and we should all now see what he did and switch and change all the codes to do what Frans is doing, which was a lot of hard work. And some people actually started doing that, changing all their codes. But then a few months later, 2005, 2000, or even 2006, two groups in different parts of the United States, in NASA Goddard and Brownsville at the time, managed to do the same thing as Pretorius, but with all the same techniques we've always been using. They use the same techniques. They even use the same code. The group at Brownsville was using the same code we were using at the Albert Einstein Institute in Germany, the exact same code, but realized there was a key element we were missing. We were, as I was saying, we were trying to glue the center of the black holes to the grid because the centers have infinities, and the infinities are difficult to deal with, so we dealt with them analytically. We took them out of the simulation. And their idea they had, well, why don't you stop doing that? Just put the infinity there and let the computer deal with it. Okay? Forget about the infinity. Work as if there was no infinity, and just allow the black holes to do whatever they want. This was very scary. Because if you have an infinite thing in a numerical simulation, of course you never have the infinity there because the computer wouldn't work. You put the infinity in between points. But you have very large numbers. You have a peak, a large peak in the function. So you have a large peak in the function and you do numerical analysis. You immediately think, my God, if this is very large, the errors are going to be huge. And if I increase the density of the points, then I'm going to get closer to the infinity, which means the errors are going to be even worse, close to the infinity. So this is something we shouldn't do. So all your intuition as a numerical person told you this you shouldn't do. You shouldn't try to move an infinity through your grid. It's going to cause chaos. It's going to destroy all the simulation. It's going to make your errors huge everywhere. It's never going to work. But it did work. And essentially the reason it works is because these are black holes, and the infinity is inside the black hole, and nothing leaves the black hole, not even the errors. So this actually does work. It converges, but it's something we didn't know. So these people just tried it. Let's see if it works, and it worked. And for a while, a lot of us were thinking, this can't be. This is surely wrong, but it wasn't. It worked. So after that, it's one of those things you want to bang your head against the wall, because it was the same code everybody else was using, the same code we had in Germany, the same code I had in Mexico, and what they did amounted to just changing one line in the code. Literally one line. Don't do this. That's it. And they worked. So I'm going to show a few of those things. I wanted to show just this picture that I showed yesterday for those of you who were there, to show that NCSA was really very much involved on those things. Gabrielle and I came to visit back in '93 when we were trying to do the simulations. Ed and Waimo went to visit us in Wales the same year. We were all trying to do these simulations. I'm going to show some of the early simulations here. This is one I showed also yesterday, but I have a few more movies about the simulation. This is a simulation done in 1995, I think, at the NCSA with that group. It's a head-on collision still. It's not an orbit. It's the collision of two black holes head-on. You can see it's very quick because this video is not very good and it's very, very fast. You will see two depressions. You will see a sheet and two depressions. Those two depressions represent the two original black holes. They collide very quickly. They fuse into a bigger black hole, and you'll see a line suddenly there that represents this final black hole. And you see many colors going out. Those are the gravitational waves. So the first one I wanted to show is this one. Those are the two black holes. You see two depressions. They merge, and you see all these colors coming out. These colors represent the gravitational waves going out. Two black holes are colliding head-on, so there's actually a symmetry around the line that connects the two black holes. So you have to imagine in your head that you can rotate the whole thing. So these things that look like bananas coming out actually are tori, right? Coming out on the direction perpendicular to the line connecting the two black holes. So that was the simulation from 1995. The other thing I wanted to show you is they actually did a lot of analysis on that simulation. They found out the horizons of the black holes, how they merge. This is an image of that collision again. You have the two black holes. These green surfaces are the horizons. And again, these colors represent the gravitational waves coming out.
That's actually the 3D version.
That's a 3D version, yeah, that's true. I should have said that. This is a head-on collision, but it was done in a three-dimensional code. It's different from what Larry Smarr did in the 70s. That was a head-on collision done in an axisymmetric code, a two-dimensional code. This is a three-dimensional code reproducing the same results. And you can see, so I'll play it again. It's very quick. They merge like two drops of water, and you see the waves coming out. Okay? This thing you see at the end is nasty noise, is because the code is about to crash. That's what would happen with the simulations. The errors would accumulate and the code would eventually crash. And I'll show you another one, assuming it's here. Generator spans. Well, this one is nice. This is something that Steve Brown did at the time. This is another view of how they merge. This is the horizons, and they collide and they merge. And then we go around. The rotation is not real, okay? It's just so you can go around the whole thing to see what happens, right? This is another simulation that was done later. This one was done in 1999. I talked about it on the timeline. It's the Grazing collision, two black holes colliding, not head-on, slightly offset, with slightly different sizes initially. If you see one is a little bigger than the other, this is the horizon. The colors represent the curvature of the horizon, but don't pay too much attention. Just think that those are two black holes that will collide, slightly offset. And this is seen from a distance. There it goes, now it's working. You see, they collided, a new horizon formed, they've merged, and then it grows. Now, this growth is not real. This is what I mentioned. Once they collide, the black hole settles down very quickly to something spherical and just sits there. But as I mentioned, the black hole swallows everything, including your coordinates, including the observer sitting there saying, I am r equals 10, and I'm outside the black hole. And eventually he says, I'm r equals 10, but now I'm inside the black hole. It's not because the black hole grew, it's because this observer fell into the black hole. Okay, so this growth is really just apparent, it's not real. You can see the same thing here from a distance. The whole grid is here. They merge. And you see here, these colors are the gravitational waves. I'll show it again, because this picture is extremely interesting. We learn a lot from it. So you see what's happening here? You see these lines? This shouldn't be there. Oh, sorry. And let me advance it a little bit more. And you see now, there's even more lines all over the place. You can see a grid of lines. That grid of lines shouldn't be there. This simulation was done in a cluster in which you send to each different processor little pieces of the simulation. And what you're seeing is the boundaries between the processors. What you're actually seeing is an error in the code, a bug, that is not doing properly the communications between the processors. But you wouldn't notice from looking at the code very easily. You notice from looking at the visualization. That's one of the things visualizations are very good for. They show you errors you didn't see on the code. When we saw this, we immediately said, oh my God, this is wrong. What's happening here? And it's the boundaries of the processor. There must be a bug in the code. Go and look for it, and we found it. Okay? So that's why I like to show this simulation, because we learned from it. And we fixed it. So there's a nice movie of when that doesn't happen, but I'm not going to show it. And then at the end, you also see something else. Again, a lot of horrible noise coming out here. That's numerical error, and that's because the code is about to crash. And then it crashes. Okay? It fails. That's what happened to all our simulations before 2005. After a while, the code would just fail. It would crash. The errors would kill you. We could extract a little bit of the gravitational waves from this simulation. And then by 2002, we actually were contacted by the Discovery Channel, who wanted to do a movie and a program about the collisions of black holes and this simulation. So they did a movie, a very beautiful movie, one of the best simulations we could do at the time. It was a state of the art then. You probably won't be able to see it, because that's something I never understood. The people of the Discovery Channel insisted that black holes should be black. So the black holes, one is here, and the other one is sitting over there. And you can't see them because the horizon was painted black. And that's because they said that you can see the black hole there, you can barely see it. And so it doesn't really show the horizons very well because they insisted on them being black. But all the colors are the gravitational waves coming out of the system. This simulation did less than an orbit. It was one of these innermost stable circular orbit things, so they did only about a quarter of an orbit, maybe a bit more, and then they collided and then fused, and we can see all the waves coming out. This is a three-dimensional simulation. It was the state of the art in 2002, the best we could do at the time.
By the way, that was visualized here. When Werner came over here and worked with the team.
Yeah, that's true. Many of these things that I showed you, especially this one, the last one, the Grazing collisions, the visualizations were done by Werner Bender, who was a wizard in these things. He's still doing the new ones, right? Then came the first breakthrough, 2005, as I mentioned, Pretorius. He solved the problem. He could do several orbits. Don't really worry about too much. The important thing about this is everything was different. Everything we had worked for 20 or 30 years was totally different. This code, this way of doing things is still around, and Pretorius is using this, and other people are doing similar things. But many of us were really very disappointed at the time with ourselves, thinking everything we've done doesn't work, we need to do everything different. But it wasn't true. As I mentioned, in 2005, there came the other breakthrough, doing everything we've always done, everything we had invented in the last 20 years, with the exception of this very last idea of allowing these points with infinite values of the gravitational fields to do whatever they wanted on the grid. Let them loose, let them fly. And as I mentioned, it amounted to deleting one line in our code. But it worked. And we didn't think of that ourselves. Manuela Campanelli and her group and people also at Goddard also had the same idea. This is a simulation, one of the early simulations they did with this idea. So I'll show you this from 2006. This is Manuela Campanelli's group. I'm going to show you this simulation, the collision of black holes. The visualization is different. In the other ones, we showed the horizon of the black hole. This one doesn't show the horizon. It just shows the intensity of the gravitational field. So you see in the middle, it's essentially going to infinity. It's very, very large. Okay? There's two black holes going around 2 or 3 times, and then they coalesce. Okay? This is one of the early simulations. It's also very, very beautiful. We also learned something from these visualizations early on, which we didn't know. If you notice, the peak here is very big, and it very quickly drops. Just look at it. Whoop, now it's about half the size. This is something that's really happening in actually the solution of Einstein's equations. This is a singularity that blows up as 1 over the distance to the center. That's the initial data. The initial data we built has this type of singularity that goes as 1 over r. Very quickly, it changes character, and it becomes a singularity that blows up as 1 over the square root of r, which is different. And it's not a numerical error. It's really what the things are doing inside the black holes. And we learned that also first from the visualizations, and then we understood it from a theoretical point of view, that the whole character of the singularity is changing. That whole coordinate condition is driving you to a different situation very quickly. And this was seen from the simulations. This one shows the gravitational waves coming out of that simulation. It's also a very early visualization. So you see now the waves coming out. This is another simulation from around the same time, but done by the Jena group in Germany with a very different code, but using the same ideas. Used to show you that by that time, essentially everybody could do it. Once the breakthrough was there, we all knew what we had to do. But also to show you that the simulations require very, very high resolution. And the whole structure of the numerical grids here is very interesting. So we'll zoom into the grids. See, each grid has twice the resolution as the previous one. It's about 7 or 8 levels there. And then there's the finest grid following the black holes. This is what people still do. Because of these very huge peaks, essentially infinite, it is true that the error doesn't really leak out of the black holes, but that's only true if your resolution is very high. If your resolution is low, some error does leak. So you need to really resolve these peaks very, very accurately. So you need to have a lot of resolution around the peaks. So this code uses 7 or 8 levels of refinement. Okay? What came out of these simulations, this is also from around that time, 2000, and a little bit later, maybe 2008. This is not as beautiful a visualization, but you learn a lot from simple diagrams as well. This diagram shows, again, the black hole collision, in spiral black hole collision, and you're tracking the center of one of the black holes. Not 2 of them, because if you put the other one, you just get all tangled, right? You get 2 spirals all tangled up. So this is just the center of one of the black holes. It goes around many, many times, approaching, slowly approaching until it fuses with the other one and goes to the center. Okay? So this again shows about 7 or 8 orbits. And these are gravitational waves coming out of that system. You can follow them. They increase in amplitude and frequency. We call this a chirp. Then they collide here, and very quickly the final black hole oscillates a bit and settles down. This is another view of similar thing. This is actually from another code. This is the Caltech code. It's called the SPEC code, which uses very different techniques, and it's actually much cleaner. The way from this code is much more precise. You can see here many, many orbits. You see the chirp, then the collision, and here is a zoom to this very small region. When the last 2 or 3 orbits, the collision, and then the final black hole just oscillating until it settles down. Now, I show this because you need to keep this in mind. This picture is the one you really want to keep in mind. We had this picture in mind for the last about 10 years, and we know what happens. But I'm going to show you another interesting thing that people have been doing in the last few years that it became very important around 2008. People discovered the first simulations were black holes that were identical. We needed to do the black hole collision initially with identical black holes. Why do you complicate things even more if you can't do that, right? So we did identical black holes, and they collided. But then people started looking at black holes that were not identical, different masses, maybe the black hole spinning, maybe spinning in different directions. And they discovered whether when the situation was not symmetric, you had different black holes. For example, this one's bigger than the other one with different spins. The final black hole, once they merged, would shoot out in a different direction. Yeah, it had linear momentum. We call that a kick, a gravitational kick. Now, if you don't really know much about gravitational waves, you would be surprised by this because you would think when the 2 black holes were here, there's the center of mass here, the final black hole just sit there. But it doesn't, it flies up. So what's happening? Are we not conserving momentum here? Of course, if you think about the gravitational waves, you are conserving momentum. The gravitational waves carry away momentum, not only energy and angular momentum, but also linear momentum. So after the collision, the gravitational waves have a non-trivial linear momentum, and the final black hole goes away, and it goes away at hundreds of kilometers per second, maybe even 1,000 kilometers per second in some cases, and you can push it up all the way to 2,500 kilometers per second. I'm going to show a simulation of that. This is called the super-kick. It's a very special configuration. 2 black holes in orbit, each one spinning, but the spin of the black holes is on the plane of the orbit, so they're actually spinning like this and like that, and in opposite directions, and orbiting like that. Okay? That's the initial condition. And this is the simulation for that system. That's also done by Manuela Campanelli's group. They gave me this file. So you see the 2 black holes, they orbit. You see the plane of the orbit is oscillating, which is already very interesting. They collide, and that's the final black hole, zooming up. This is what comes out of the simulation. You might think this is just an artifact of the simulation. It's not. The black hole actually has linear momentum. It's moving up at 2,500 kilometers per second. Okay. So it's called the super-kick. This is interesting because the escape velocity of very large galaxies is about 2,000 kilometers per second. So if this is true, this black hole would leave the galaxy. It would go floating into interstellar space. Now, this configuration is very special. We don't expect these configurations to occur in nature, at least not very often. Now, this is something I mentioned quickly yesterday. The gravitational waves are oscillations of space-time. They are not sound. Don't be confused. But they are oscillations of space-time, and you detect them by these mirrors oscillating. So you can plug the output of the detectors into speakers, and in principle, listen to them because the frequencies, by coincidence of these types of systems, are in the audio range that we can hear. So if you do that from the simulations, you should hear this. Now let's hope this works. Oh, wow. It was working a minute ago again. Let's see. No, so let me get out and see if I can do it from here. Yeah, over. Let's see. This is the collision of 2 neutron stars with 1.5 solar masses each. This is how it should sound. Okay, that's it. Again, the file is very long. I don't know why, but we only want to listen to the end. Okay, that's how it sounds. That's how it should sound. This is 2 black holes, 2.5 times the mass of the sun. Okay, and this is 2 black holes with 50 times the mass of the sun each. That's how it should sound if you could listen to it directly on the speakers. Now, this is very clean because this is data from a simulation, okay? This is what comes out of the simulation. It's very clean, but I'll show something slightly different in a minute. Now, this is what we could do. The simulations in the last 10 years have gotten more and more sophisticated with different masses, different spins, more computer power, more precision, but it's essentially the same idea. And we've been waiting to test if these simulations were right for quite a long time. For a while, this is interesting, there was even a bet with Kip Thorne and I don't know who else.
With a whole bunch of us, and
Yeah.
Kip has decided to concede the bet. So,
Yeah.
so Richard Wymo and I are the first three to sign this, but there are about 30 people, and it went around a few of us to figure out. There were a few signatures there who we couldn't quite figure out who they were, but we worked it all out. So Kip apparently owes us a bunch of bottles of wine, I think.
So the bet was who would be first, the numerical people doing the simulations or the gravitational wave observatories detecting something. And there was a race. And that, even in 2000, the race was still on. We didn't know who would win. Well, we won. Well, not we, but the people that actually finished the simulations. But the numerical relativity community won. We could do the simulations about 10 years before the waves were detected. But the waves were eventually detected. And this is what they detected. And this announced 3 weeks ago that they detected gravitational waves for the very first time in history on 14th of September 2015. It was announced 11th February 2016. This is the detector, the signal from the detectors. Now remember this? I told you a few slides ago you should remember something like this. It's exactly what they saw. This is one of the detectors in LIGO. This is the other detector in LIGO. If you superimpose them, you see there's the same signal. And this is a simulation of the system they saw. This is the signal you should see. According to the simulation, this is what the detectors see. There's a lot of noise, but that's what they see. Okay. And this is the simulation, okay? So this is beautiful because it's the collision of two black holes. People that are in this field, you saw that and we would know that this is the collision of two black holes immediately just by looking at it. I'm going to just give you the sound of this. I hope. That's the collision. That's the output of the detector connected to speakers. You can listen it twice because first is the original sound, but the original sound you just hear a lot of noise and some very quickly. It's very hard to hear. But then they shifted everything in frequencies to what is easiest to listen. So I'll play it again. You see? And that's when they shift the frequency. So this is what was announced a couple of weeks. This is a simulation of that, so I only have this transparency to go, and that's it. This is the simulation of the collision. This is a visualization that I got from the LIGO page. Again, the two black holes going around and around. These are the gravitational waves. They become more and more intense as the black holes get closer and closer together. And eventually, they will just coalesce. You can download this from the LIGO webpage. It's there. It's a simulation of this system. Closer and closer. Faster and faster, they coalesce. There's a last burst of gravitational waves. And then this settles into a rotating curved black hole. So I'll just leave you with the conclusions. Numerical relativity has come a long way. It's actually now 5 decades, not 4 decades. This is wrong. And it's now however, it's a state of maturity. We have a very deep understanding of the theoretical issues in the field. That was very important. The formulations, the well-posness of the equations, conditions, coordinate conditions, boundary conditions, initial data, numerical methods, software engineering. That took a very long time. We have now today several advanced 3D codes around that can handle both black holes and even hydrodynamics, Newton stars. These codes are, of course, parallel, capable of mesh refinement, complex analysis tools. They look for apparent and event horizons of black holes, angular momentum, gravitational wave radiation, et cetera, et cetera. And now with the recent detection of gravitational waves, just a few weeks ago announced, we are entering a golden age. I think we're now really doing astrophysics. For a long time, we were just theoretical physicists playing with computers. Now we're becoming astrophysicists because there is real data out there. So that's a very, very exciting time. So I end up there. Thank you very much.
Thank you, Miguel. I think that was a great illustration of how hard this problem was for so many people for so many years, and now it's paid off, all that work,
Yeah.
great work. So Miguel has a flight at like 1 o'clock.
Yeah, in about an hour.
So if there's a burning question, why don't we have 1 or 2 questions, but with quick answers, and then we're going to have to escort him off to the airport quickly. Adam.
How important is it to assume that these are actual singularities, that there's not some more exotic, denser matter than like neutronium or something inside of black holes?
For the final form of the waveforms, it's really important for most of it. I mean, this is what you get from 2 black holes. If you put a neutron star, the initial part looks the same, but the end is very different. And if you put something exotic like that, I don't know, we haven't done it, but the thing is, it looks very different when they collide. Because when these things collide, they produce a new black hole, and the black hole, we understand what it does. A very distorted black hole produces this very characteristic signature. We call them quasi-normal modes. It's sort of ringing down at the very end. That's only a black hole. Anything else won't do that.
So we actually then have empirical evidence that it's an actual singularity.
This is very strong empirical evidence that these are real black holes with those masses, and in the end we have a real Kerr black hole rotating. We don't know of any other system that can reproduce the whole thing. Initially, if you put stars, they would do something very similar, but only initially. At the end, it's very different.
And the frequency of that final black hole depends only on the mass and the spin of the black hole, and it's uniquely mapped. So you see that and you say, I know that's how many solar masses and how much it's spinning.
Yeah. No more?
Okay. What, Jeremy?
Yeah, you showed the errors there that appeared in the visualization
Okay.
that were very easy for the errors in the visualization were really easy for a human to identify. Is there also the possibility of errors that are not easy for a human to identify? That because you mentioned that looking at the code, you wouldn't have found those errors necessarily, or at least it would have been a lot more difficult. So, do you rely on the visualization to indicate the rest of the errors as easily human identifiable, or is there a chance of...
Not just the visualization. The visualization is a nice way to see general features globally, but we do very detailed analysis of the gravitational waves coming out, for example. That's not a complicated visualization, but it's a very complicated analysis tool. And from that, you get this time series that gives you the waveform. And that you can compare. You can first, within the same code, check what happens if you increase the resolution or decrease the resolution to see if that's converged. But then you can compare to other codes that were written independently by other people using other techniques and match them, and they match beautifully. So we are pretty sure that these codes are doing the right thing. And you would see an error immediately there. If one of them did something completely different to the other, you would see that one of them must be wrong or both. But they match so beautifully using totally different techniques that we are pretty sure that the results are right.
Okay, thanks.
Okay, I think just so we make sure Miguel does make it back to Mexico, we better conclude. So thanks a lot, Miguel.
Thank you.